Well, we've gotten to z-scores in lesson 2.1a, and now we're going to finish this first section with transforming data. Okay, I'm in the interrogation rooms, as we like to call them at school, and there's a little bit of an echo, so please forgive me. I'll try to keep it to a minimum. All right, when we're talking about transforming data, we've already been doing that. But it is a technical definition and something that they do note on the AP exam, so you do need to understand what transforming data is. It is a big piece, not a huge piece, but it's a piece that they will ask you about. So when we standardize a score, oops, it helps if I have the pen on. When we standardize our score for an individual observation, then what we're doing is that we are transforming the data by subtracting the mean and dividing by the standard deviation. I'm just going to put this right here. You know what that is. And what that does is it transforms transforming the units, I'm trying to remember what I said. Converts. There we go. Transforming converts the observation from the original units to a standardized scale. And we did that simply by finding a z-score. You had your x minus x bar over standard deviation. And that's pretty much at one time that we transform data. So here's an example of transforming data. So right now, this is a little question where they've taken a group of students, and this is right after they introduced the metric system as a system of measurement in Australia. They asked the group of students to guess the width of their classroom to the nearest meter. And here we go, here's the data. Interesting data. Note we have good clusters here between, what does that look like? 2, 4, I don't even know, 2, maybe 7 or 8 up to 18. And then, wow, somebody actually thinks that their room is 40 meters wide. And my guess is not the brightest on the metric system. So let's talk about this and let's practice what we've already learned and let's talk about what we see. Well, first of all, what's the shape? Well, it's bimodal. Got 2 modes. It's skewed right. And what else can we say about it? I don't know. Pretty much it. The peaks are where? The peaks are at 10 and at, it looks like 15. So there's shape. Now let's look at center. Well, the median was 15 and the mean was 16.02. So because this is skewed and it seems to have some outliers, I would choose the median for the best representation of center. Alright, what about the next thing? We do shape, center, spread. Oh yay, spread. What do I have for spread? Well, if I figure out my IQR, quartile 1 is 11 and quartile 3 is 17, so my IQR would be 6, which describes the middle 50%. I can put in things like my range, which was 32. What else do we need to know? Let's see if there's any outliers, right? So 1.5 times the IQR would be 9. So we're going to add 9 to quartile 3, which would be anything above 26 or less than, taking 9 away from 8, negative 1. So, do we have some outliers? Oh yeah, we do. The 5 number summary is going to be our best option because of the skewness in this weird outlier experience. And then what do we have? Well, our outliers, we already said, were, we had 4. So the highest guesses that we had were 27, 35, 38, and 40. Those are all outliers. 27, 35, 38, and 40. So, if we look at this, the actual room width was 13. And because we have the actual room width, we can actually find out something called the standard error. So let's look at the standard error. Okay, the actual room width was 13 meters wide, so how close were their guesses? Well, to figure out their error, and it's not standard error, it's just regular error, error is their guess minus 13. And so I have a list down here of the guess and then the error. So what we have done is taken this data here. This was the original data. Right there is original. And we subtracted 13 from it, and this is our error data, where we've included the error. So now notice, we have shifted this from a mean somewhere over here of, what was our mean, 16, to now we've shifted it over here around 3. Our median was 15 in the first set, and now our median is 2. So what happens when we subtract the 13 is we are literally just moving the distribution. But how about anything else? Did anything change with the shape or the range, spread? Well, the shape looks exactly the same. Wow, I cannot spell today. Shape. Okay, let's take that and make it a real word. Did anything change in the shape and spread? Well, if you look at it, the shape is exactly the same in both. And the spread has not changed either. So what did we do when we subtracted the error from the actual room from it? All we did was shift it down so it's closer to a center of 0. All right. So one thing that we can do to transform data is add the same number, add or subtract the same number, either a positive, a negative, or a 0 to each observation. And when we do that, when we add it to measures of center and location, it just, I have to put this center, location. So such as the mean, the median, quartiles, and percents. It just simply adds the number to it. But if we do that, it does not change the shape of the distribution. It does not change the shape of the distribution or measures of spread. So all we're doing is just moving it basically on a number line, up or down. It's just like when I say transforming data, it would be transforming a graph that we might do back in the old days when we did these things, in geometry, and we had to transfer them, say, over here. And what do? We just added or subtracted different numbers to the x and y coordinates. Same exact thing. The picture stays the same. Nothing changes. The shape, the spreads stays the same, only we are just shifting it down to a different position. So let's look at this. Suppose we take the same data about the estimation of the room width. Now, it looks like they're having trouble, because especially these guys up here, which are absolutely crazy. They're like 2 to 3 meters too high. So we're going to convert the measurement to feet. So to convert to feet, we know that there are about 3.28 feet in 1 meter. So what we've done with this data here is we've taken all of these data points, and no, I'm not going to make you do that, and we have converted it to feet. And so what happens when we do that? Well, we end up changing the shape or the spread. Notice we're still bimodal, right? But this is extremely far apart as opposed to this very compact situation. So this is our error in meters. This is what we originally started with after we did the error. And this is our error measurement in feet. Now notice how much more spread this is when we change to feet. So now it looks like these poor guys hanging up here were so totally off. All right, well, we multiplied by 1 and divided by a number basically when we did that last bit of data. So what does that do? If we multiply or divide, what does it do to each observation? Well, multiplying or dividing measures of center and location, again, such as mean, median, mode, sorry, we don't do mode, quartiles or percents. By B, and if we multiply or divide measures of spread, by the absolute value of B, because we're not going to have any negative numbers. So it multiplies them, but it does not change the shape. So it will either make it wider or make it smaller, but it will not change the shape. Does not change shape. So if we add or subtract, we're simply moving it horizontally on a number line in essence. If we multiply, we can spread it out, we can shrink it down, but we will not change the basic shape of our distribution. All right, so this is a question that's referred to, and this is on page 96 in your book. And there's a whole long story. There's a picture. You'll see this picture if you look for this in your book of the this picture right there of the cold weather, which would be kind of nice and kind of warm right now. All right, so we're going to do the data in Celsius to find the mean temperature, the standard deviation, and the 90th percentile in Fahrenheit. And then we're going to figure out what we can learn from this. Well, the first thing we have to know is how do we convert? So many of you already know this, but Fahrenheit is equal to 9/5 times the Celsius plus 32. All right, so we want to find the mean temperature in Fahrenheit. So we take the mean temperature, which is, I don't even know, what's the mean? 8.34 is our temperature in Celsius. So we're going to do Fahrenheit equals 9/5 times 8.43 plus 32. And if you get that, you get 47.17 degrees Fahrenheit. So this is the thermostat in Fahrenheit. And if you read the whole problem, basically what's happening is you have a cabin that has to stay above freezing, because you are pretty high, because you need to keep the pipes from freezing. So they have a Celsius thermometer, which is actually the thermostat, and then she has a digital thermometer that is in Fahrenheit. So we need to figure out how close these are. So if you look at this, in the mean in Celsius was 8.43, and that's supposed to be keeping it around 50 degrees. But we notice that the average temperature is 47.17, which means that something is not working well. All right, so let's multiply. Let's see, the second part I want to know is I want to calculate the standard deviation of the temperature readings in degrees Fahrenheit, and then interpret this in context. So I want to multiply each observation by 9/5. So that's the same as multiplying the standard deviation by 9/5. But adding 32 does not affect the spread. So the standard deviation of the temperature measurements in degrees Fahrenheit is 9/5 times 2.27. Because remember, we're not caring where this is. We're looking at a standard deviation. We're not moving it. And that 32 is moving it. I hope that makes sense. And what do we get? We get a standard deviation of 4.09 degrees Fahrenheit. So the average distance of the temperature readings from the mean is about 4 degrees. Well, that's a significant amount of variation going on, 4 degrees. I mean, that can make or break your pipes. And last, we want to know the 90th percentile of the temperature in Fahrenheit. Well, the 90th percentile in Celsius happens to be 11 degrees Celsius. So what is it in Fahrenheit? Well, percentiles, we're going to go ahead and do exactly what we did before, because it's not one of those things like standard deviation that we're interested in not moving, which we're just looking from the distance from the mean. In this case, we're going to use our equation again and plug in 11 for x. So we have 9/5 times 11 plus 32, which the 90th percentile is 51.8. So, adding and subtracting a constant does not change an individual data value's location within a distribution. Neither does multiplying or dividing by a constant. If you're at the 90th percentile for height, you're at the 90th percentile for height in meters. If you're in inches, it's still going to be the same. The distribution will still be the same regardless of the units. But this is a helpful bit of information because we are able to translate data or transform data, and it does not have an effect on the shape. Notice this little part. Alright, now we're moving on to density curves, which is kind of really where we're going to spend the rest of this chapter. Alright, in chapter 1, we learned some tools for describing distributions. We're really heading into some really cool distributions at this point. And the first thing we learned was to always plot your data. It is vitally important that you plot your data. You got to see it. Then the second thing we learned was to look for the overall pattern of the data. Shape, spread, center, look for outliers. We're looking at the pattern. That was step 2 in exploring our data. Step 3 is to calculate a numerical summary. And yeah, we needed to use our socks, but probably up here in the patterns. And now we're going to add one more. Sometimes the overall pattern of a large number of observations is so regular that we can describe it by a smooth curve. This is an example of a lot of data put on a histogram that is so close together that we can describe it by this smooth curve. Now, yes, it does not exactly represent all of the data, but it is generally a good picture of what's going on. So this is called a density plot, or density curve, sorry. This density curve happens to be the ITBS vocabulary scores for, 947 7th grade students in Gary, Indiana. So, key vocabulary. What is a density curve? A density curve is a curve that is always on or above the horizontal axis. And it has an area of exactly 1 underneath it. This concept is key because what we're going to be doing from now on, or for a lot of now on, is looking at the area underneath the density curve to determine the proportion of people that fall within a certain area or range. So a density curve describes the overall pattern of a distribution. The area under the curve and above any interval of values on the horizontal axis is the proportion of all observations that fall in that interval. We're going to use this a lot in section 2.2, so it'll start making more sense. Okay, this is in your textbook. I just thought it was funny because, here we go. Miss O'Malley, if you're thinking about grading our math tests on a curve, here's some curves that this kid wants. This is where everyone fails except me. This is where almost everyone fails except for me. And this is the one where the test is so hard everyone quit school but me. So, okay, I thought it was funny. I mean, how much fun can you have with density curves? But anyway, wouldn't that be fun? How many of you want the whole class to fail and you to win? You win if you get an A. No, not really. All right, so here's the cool thing about density curves. If we have a perfectly normal curve, which we might be looking at soon, you'll notice that the median and mean are exactly the same. This is a very symmetric curve, perfectly symmetric. And in fact, we're going to call this normal next lesson that we have, because the two sides are exactly the same. The area here is the same as here. So therefore, knowing that the area under a density curve equals 1, I know that the area on this side is 0.5, and the area on that side is 0.5. In other words, 50% of the data lie above the mean and median, 50% lie below. Now this is a skewed density curve. And in this case, this is skewed to the right. So the mean is greater than the median. We're always going, I can't talk, right? We're always going to put our mean on the side of the tail. So like in this case, the tail is going this way, so the mean is going to shift out a bit over here. Now, technically speaking, the mean is the balancing point, right? Because we talked about this before. It's where everybody gets a fair share. It's the balancing point of the distribution. So this should be where everybody feels the same. So you'll notice if I put my mean up here in this distribution, well then there's too much weight back here and it's not going to balance. If I put my mean here, obviously that is not in the right place. It's going to fall down because there's too much space up here. But in this case, I put my mean precisely in the perfect place in order to balance my density curve. So it's literally just a balance point. All right, let's look at this. This is a density curve, and we want to look at some questions. This is actually Check Your Understanding on page 103. And I want to explain why this is a legitimate density curve. Well, this is a legitimate density curve because, 1, the curve is positive everywhere. And 2, the area under the curve, the total area under the curve is 1. Now, the next part, what proportion of observations lie between 7 and 8? Well, they're pretty nice. They tell us the area between 7 and 8 is 0.12. So 12% of observations lie between 7 and 8. All right, so now on your notes, trace the approximate location of the median. Well, the median, we want to be the middle of the values. So it's about right here. This should be the median. I'm going to put an M down here for median. And mark the approximate location of the mean. And how do we know which way where the mean is? Well, remember, we know that the mean has to be this direction because the tail is that direction. So the mean happens to be somewhere right along in here. So that is my mean. So why does the mean and median have the relationship they do in this case? They have this relationship because this density curve is skewed to the left, and therefore the mean will be less than the median. All right, that pretty much sums up this quick little part of the lesson, and we will be finishing up our homework next class, starting on normal curves. Normality. Is that a word? Hope you guys have a great day.